The debate between run-of-the-mill for loops and list comprehensions has always been a popular topic among Python programmers. Over the next 4 minutes, we're going to disassemble and dive into the bytecodes of each approach, explore the inner mechanics of the call stack, and introduce alternative ways to construct lists that pack even further performance gains. Let's get started. Here we have a traditional for loop, as well as a list comprehension that serve the exact same purpose. Say we want to create a list where we double each number in another collection or iterable. The for loop has a runtime of 437 microseconds, while the list comprehension has a runtime of 335 microseconds. This is approximately a 30% performance boost when using a comprehension. It turns out Python's interpreter optimizes the bytecode instructions generated for list comprehensions, resulting in more efficient execution. The Python interpreter is able to optimize the comprehension as it knows the exact operations that will be performed ahead of time. Before we go deeper, let me introduce the concept of the call stack. The call stack is just a stack of stack frames. Each stack frame corresponds to a call to a function or method which is not yet terminated with a return statement. Each stack frame sitting in the call stack is in a suspended state and is waiting for its turn to resume execution. This is going to be more helpful to cover with an example. During regular execution flow, each time a function or method is invoked, the current function is suspended and the called function now becomes the newest stack frame on the call stack. It will remain the topmost frame on the stack until it is terminated, at which point control will return to the caller. One of the main reasons why list comprehensions can perform much faster is because the process of suspending and resuming a function's frame, such as when we call the .append method, can be quite expensive. Of course, when we look at our raw Python code, we can clearly see that we don't need an append method for list comprehensions, but how does this look under the hood? Let's go ahead and disassemble these code objects using the dis module to take a look at the underlying bytecodes. When we use a for loop, we can see that within the loop body, we use the load fast bytecode instruction to load the value of a local variable from the current function's local namespace onto the Python stack. We then use the load method instruction to look up and load the .append method. Both of these operations are performed within each iteration of the loop. The comprehension, on the other hand, as we can see, still implements a loop. However, it doesn't have to look up the list and its append method on every iteration. Instead, there is a special bytecode instruction, list append, that will append the current value to the list that you're currently constructing. In this instance, this results in a performance improvement of approximately 30%. The last thing that might be worth mentioning is the map function. Map can be used to create a new list by applying a function or method to each element of a collection or iterable. Map can have significant performance advantages compared to loops and comprehensions, as the entire underlying implementation is done in C. The performance of map can vary greatly based on the specific use case. For instance, if we were to use map in this example, we would need to define a separate function that contains the logic for doubling, as we cannot use inline code with map. This results in a significantly longer execution time of 664 microseconds, as we are burdened with the overhead of calling a new function for each list element. If we had a use case where we needed to call a function or method regardless, such as if we wanted to call .upper for each string within a list, we can then see a performance advantage for map, as all of the underlying logic is now pushed down to a speedy C implementation. Hopefully you are now more familiar with the differences between loops, comprehensions, and the map function, and will be a slightly stronger Python developer going forward. Thanks for watching.